Without further delay, I will hand you over to Gillian Groom to begin the webinar.
Thank you, Mark. Today, I want to talk about the impact of collecting more data has on creating insightful control charts. The topics I want to cover today are, firstly, I'm going to give a brief overview of a control chart. I then want to have a look at the situation where you're collecting complete data versus control charts and look at the contrast their different objectives. Through the use of an example, I want to talk about a key issue in creating your control chart, and this is the subgroup. I want to illustrate to you the curse of the false alarm, which can occur when you choose an incorrect subgroup. I also then want to go on to talking about complete data versus sampled data and the impact it has on control charts. And finally, I want to give you some recommendations for some insightful control charts with complete inspection or a full data set. So let's have a look at the features of a control chart. If you have a look at our example, the thing we are measuring about our process is on the vertical axis. You can see that it says sample mean, and we're plotting our results against time. This is on our horizontal axis. This is just a special kind of time series plot. The blue dots are measuring our process. These are our process measurements. Where they are blue, it is showing the process measurements that are in control. Where they are red, these indicate sources of unusual variation. You will also see there is a green line on your chart. This is the average, the total average for your process, the data we've collected. And the red lines are our upper and lower control limit, which are typically calculated from our data. Any parts or blue dots that fall within the upper and lower red lines are in control with respect to the size, in terms of whether they're extra large or extra small. If they're extra large observations, they will appear above the upper control limit. If they are extra small observations for your process, smaller than we would normally expect, they're going to fall below the lower control limit. So today I want to specifically talk about complete inspection versus control charts, and I want to compare their objectives. So let's talk about complete inspection. So nowadays, we are very lucky that we are able to collect complete data on our parts, complete measurement data of our parts. This allows us to do product inspection of all the parts, and for every single part, compare parts to the customer specification. And of course, that allows us to reject bad product before our customer even sees it. This is wonderful in allowing us to immediately identify problems with our process that may result in customers getting bad product. So this is a fantastic tool to ensure our customers are getting the right product of the right quality. Let's look at control charts. Control charts, their objectives are completely different. With a control chart, we're trying to understand the trend over time of the variation that's occurring in our process. We want to be able to separate the common variation. This is the variation we expect to see in our process, from the special cause variation. And this special cause variation may occur because of a problem in our process, but it may also occur because we have changed something in our process for the positive. But we want to see over time how these changes affect our process. They are an easily interpreted visual analysis of the process stability. So we want to ensure that they allow us to effectively understand this process stability. To illustrate the challenges that full data brings to a control chart, I'm going to simulate some results from my parts factory. This is going to be my process. So in my parts factory, I'm making 100 parts an hour, 8 hours a day, 5 days a week. And I've collected the data for 4 weeks. This results in 16,000 observations. My process is stable. And from this process, I know that the stable process has a mean of 0 and a standard deviation of 1. So what happens when I create my first control chart? So what I have done is, in this control chart, I have plotted all the individual values, all 16,000 values. This is the same as using a subgroup size of 1. Each blue dot represents the observation at each of those 16,000 points in time. Each red square represents an observation that is out of control. And you can see on my charts, the bottom one is looking at the range and the top one is looking at the individual values. And you can see that there appear to be a lot of red values. We're seeing very many red points, but this is somewhat confusing because my process is stable. I created the data, I simulated this data to ensure that it was stable. So if this process is stable, why have I got so many out of control points? This is the curse of the false alarm. So when we do a control chart, we can set a number of rules or tests for special causes. You can see in my chart here, I've summarized the 2 tests that I've used in Minitab for the charts I've produced. The first one is points more than 3 standard deviations from the center line. So these are the points where the observation is either above the upper control limit or below the lower control limit. Its purpose is there to detect sudden shifts in the process. However, with this rule, there is a probability, a chance of a false alarm, and the chance of a false alarm is 0.27%. This equates to 3 in 1,000 points. The other rule I've applied is I have looked for smaller shifts or trends by picking up 9 points in a row that fall on the same side of the center line. In this case, the chance of getting a false alarm is 0.39%, which is 4 in 1,000 points. I now, looking at my previous chart, have over 100 observations that could be a problem, which are not really a problem in this 4-week period. This brings me on to why subgroup matters. In the example as I've plotted it so far, I've treated each individual measurement as an individual subgroup. But is this the right thing to do with complete data? Before I come on to looking at my analysis and trying different subgroups, I just thought it was important to recap what is a subgroup. If we are collecting only a single observation at a specific time, there is no logical subgroup. However, if we are collecting multiple observations close together, we can treat them as a logical subgroup. In my example, I know that I am creating 100 observations an hour, 100 parts are being made an hour. My process data has 16,000 observations, and my process is stable. But when I was using a subgroup size 1, I was getting a number of false alarms. Just to evaluate this, I'm going to have 43 false alarms for test 1 with 16,000 observations. To get this number, all I did was multiply 16,000 by 0.0027. This is the 0.0027% a false alarm rate for test 1. You can see for test number 2, if I multiply 16,000 by 0.3039, I get 62 false alarms for test 2. This also means using a subgroup size 1, producing 100 parts every hour for 8 hours a day, I will get a false alarm every 1 hour and 26 minutes. The result of this, the wrong choice of my subgroup, results in too many or too frequent false alarms. And of course, if I keep having false alarms, the users are going to start questioning or believing that my charts are not worthwhile and start to ignore them. This then destroys the value of this most useful tool. So what's the fix for this? Well, we need to think more about choosing the correct subgroup size. What I decided to do was treat each hour as a subgroup. This seemed quite sensible, that each hour of the day is a logical group where the data should be similar. I'm collecting 100 data points an hour. So my subgroup size in this example is 100. When I have a subgroup size of 9 or above, I'm going to create an X bar S chart. You can see the X bar S chart that I've created. In the top chart, each blue dot represents the average for each hour of my process. In my bottom chart, each point uses the standard deviation within each hour to represent the variation. I'm still using my full data set, but you can see in my results that treating each hour as a subgroup results in a clear understanding of my process. And you can see now that I'm getting the results I was expecting, given I already knew that my process was stable. There are no red squares on this distribution. You can see that my process is in control. All of my points are within the upper and lower control limit, but also there are no other tests that have been failed because there are no red squares on my chart. The other point I want to talk about is, do I need to actually do this analysis with the full data set? So in the previous slide I showed you, I was still using the full data set. I was just using the subgroup size to be the hourly data, so 100 data points. So do I really need to use the full data set? So I did some testing on if I would get the same results using sample data. And I tested the following. I'm still treating each hour as a subgroup, but instead of taking the full 100 observations, I tested the following. I first of all said, let's just take one random observation per hour and create an IMR chart. I then did a selection based on selecting 8 random observations per hour, and in this case the correct chart to use is an X bar R chart. And then finally I selected 9 random observations per hour and created the X bar S chart. This is the same chart I produced using 100 data observations. The things I wanted to check with the sampled results were, I wanted to check that the estimate of the variation would be 1, because I know my simulated data has a standard deviation of 1. The estimate of the mean should be 0. And the number of special courses should be 0 because my process is stable. So for each of these options, I check these 3 metrics. So let's have a look at the first result. So in this case, I've selected at random 1 observation per hour, which results in 160 measurements. You can see on the chart, if I look at the top chart and I look at the mean for this process, you can see that the mean is slightly above 0, which is what I was expecting it to be. You can also see on the top chart, there is one item, one observation where it appears to be out of control, is larger than our upper control limit. However, 1 out of the 160, I think I could live with. Let's have a look at the bottom. So because this is a IMR chart and we only have 1 observation per subgroup, instead of using the range or the standard deviation to estimate the variation, the only choice we have is to use the moving range. And you can see that the moving range, on the far right-hand side, is a pretty good approximation to our standard deviation, which should be 1. So looking at this sample data, I've got 1 point failing the test. The estimate of standard deviation is good, but the estimate of the mean is not quite as good as we would hope. Let's move on to taking a sample based on 8 observations per hour. So if you have anything between 2 and 8 observations in a subgroup, instead of doing an IMR chart, you're going to do an X bar R chart. So this is my result of my X bar R chart, where I took a random sample of 8 observations per hour. If I have a look at the top chart, you can see that I have a better estimate of my mean. If I look on the far right-hand side, you can see that the estimate of the mean is 0.046 compared to 0.1 when I was looking at my IMR chart. So this is a better estimate of my mean. When we look at the bottom and we see the sample range, you can see that the estimate, that the range, the average range is 2.98. However, to change this into an estimate of the standard deviation, we need to do a calculation, and we need to divide the range by the bias correction factor for this subgroup size. And you can see here 2.908 divided by this 2.847, which is this bias correction factor, gives me a value of 1.02. A pretty good estimator of the standard deviation. So my results, I'm in control, the estimate of the mean is good, and the estimate of the standard deviation is good. So I can conclude for this, yes, instead of using the full data, it would be reasonable to take a random sample of 8 observations per hour. Finally, let's have a look at increasing it. Instead of 8 observations per hour, let's have 9 observations per hour. As soon as your subgroup size is 9 or above, you're going to use an X bar S chart instead of an X bar R chart. The only difference between an X bar S chart and an X bar R chart is that in an X bar R chart, you're using a range to estimate your variation, whereas in an X bar S chart, you're using the standard deviation to estimate the variation. If I have a look at my top chart and I look at my mean values, you can see they're all in control. And again, I have an even better estimate of my mean at 0.024, given my mean should be 0. If I have a look at my S chart, you can see that I do actually have one outlier on my S chart. There is 1 point that is out of control, has failed the test for being outside the upper and lower control limits. But I think I could live with that. You can see also that my mean, my standard deviation at 0.948 is a good estimate of my standard deviation. Again, I can conclude that I could do my control chart with just a sample instead of my full 100 observations each hour. Well, that's very well and good. In this case, I knew that my process was stable. And I think I can conclude that sampled data is just as good for checking if our process is stable and in control over time when my process is stable. But what about if my process is not in control? The question I need answering is, do you get the same results with sampled data and an out of control process? So again, I did some simulation. I have created some data where there is a 1 sigma shift in the data. If you have a look at the chart I've produced here, this is my new data. For the first half of the data collection time, my process is performing at a lower level than in the second half. You can see that my sample mean is around 0 for the first half, and my sample mean is 1 for the second half. So you can see the shift quite clearly on this chart. The standard deviation has not changed. So in this process, the standard deviation is staying at the value of 1. With this 1 sigma shift, I've increased the mean from 0 to 1. So what happens in this chart, what I've done is I've just, apologies, but just swap back for a moment. In this chart, you can see the control limits have been calculated on the whole time period. What I've done to make this a little bit easier to interpret, in the next chart, I've changed the control limits such that we have one set of control limits for the early part of the data and one set of control limits for the second part of the data. This is quite easy to do in Minitab using the stages function. So what I want to do is see that my process is in control both before and after. You can now see that this is fully in control. This is with my full data set. So what happens if instead of using the full data set, I use a sample? So this is showing the results based on the 100 data points per hour. You can see the shift is fully reflected. But do I get the same results with the sample data? So I've done an X bar S chart. I've taken a sample, a random sample of 9 observations per hour. And you can see for the first part, the first half of the data collection, my mean is around the 0 point. And you can see in the second half that my mean is around the 1 point. If you remember, by doing this 1 sigma shift, I've shifted the mean from 0 to 1. So I'm seeing what I would hope to see given this shift has occurred. Just want to double check my sample standard deviation, and you can see this is again in control, and my estimate for my standard deviation is around the 1 mark, which is what I expect it to be. The good news is that the shift is reflected in the estimate of the mean and in the standard deviation. So what am I concluding from all of these simulations that I've done? And what are my recommendations for insightful control charts with complete inspection data? So first of all, IMR charts with individual observations should not be used. The false alarm rate is too high. You should choose a logical subgroup. In my example, I chose the hour to be my logical subgroup. So when I produced my X bar S chart with a subgroup size of 100, I could clearly see the trends in my process over time. I was not being plagued by the false alarm rate problem. You can carry on producing your control charts using your full data. However, if this is not practical, it's still possible to use sampling and get a good understanding of the trends in your process. So when I sampled 9 observations per subgroup, it gave good results for both stable processes and sigma shifts. A final point which we haven't been able to talk about today is about the use of automation via macros to automate control chart production within Minitab. So in conclusion, does more data mean more effective control charts? Well, the truth is, if you use the individual measurements that you're collecting from full inspection, it does not mean more effective control charts. It will just result in a higher than expected false alarm rate. Therefore, you still need to think very carefully about what your subgroup size should be. You can then either, once you have got the correct subgroup size, you can either use the full data, or if this creates practical problems, sampling your subgroups with a subgroup size of 9 or above will give you just as effective results. Thank you for paying attention to my webinar.